Hello and welcome to Empowered Learning. This video is the second video in the series of videos I'm making for variation of parameters. If you watch my part 1 video, one of the things I mentioned is that the part 2 video was going to be a deep dive into the derivation of it, but that video got a little long, so I'm going to use that as part 3 versus part 2. I'm going to finish doing the examples that I had planned on doing for the part 1 video in this video so that it could be broke up some. So if you're looking for how to actually derive variation of parameters method from scratch, then you want to do the part 3 video. If you are looking at just looking for an overview of what variation parameters is about and to get a few examples, then go to the part 1. If you're looking specifically for just examples of variation of parameters and not a whole lot of this is what it's about and this is how we actually kind of put this together, then this is the video that you want to watch. So in this video in particular, I am going to solve more examples using variation of parameters using both the traditional way, which is using systems of linear equations to solve, as well as the formula way of doing it. But I'm going to start off concentrating on Euler-Cauchy types of equations first, because this method will work for those types of equations too, since Euler-Cauchy equations are actually is a subcategory of a nth order linear homogeneous or non-homogeneous equation in this sense, since our G here is going to be something that's not 0. Okay. So my point is that these work for traditional linear ordinary differential equations where the coefficients are all constants, as well as for Cauchy-Eulers when all of our coefficients aren't necessarily constants as well. All right, so let's look at this example. So we want to do this the traditional way. So this means that we're going to be doing this via solving systems of linear equations, and I'm going to use the substitution method to find out what my u prime and my v prime are. If you're unfamiliar with what I'm talking about, you want to go to my part 1 video when I say traditional way and using substitution method. Okay, so you want to stop this video, go to that, and then come back to this one. All right, so to start us off here, since we're doing this the traditional way, then we know that we want to use our system of equations here. So I'm just going to go ahead and write out what it is that we're looking for. So we're going to have our u prime and then y1 plus v prime y2, and that's going to be equal to 0. We also have u prime y1 prime plus v prime y2 prime, and that's going to be equal to our G divided by A, which we'll specify here in just a second. So the main goal here is we want to solve this particular system of equations for u prime and v prime, so that from here we know that our u is just going to be the antiderivative of u prime. V is the same thing, antiderivative of this, and end result here is that our particular solution is going to look like this. Our homogeneous solution, we'll find that out before we even do all of this business here, will look like this. And our total solution, which is what we're going to be looking here for, is going to be basically a sum of these two. So to put everything in a nutshell, this is what it is that we're trying to do. Okay. And of course, finding this is what we'll actually do first. We could do it later, but we'll choose to go ahead and do it first, just so that once we get to this part, which takes a little longer than it does to do this one, we can just go straight into our answer. So I'll go ahead and separate this. So now that we know what our game plan is, we'll go ahead and start with the problem. So first thing that we want to do is find our homogeneous solution here. So notice that we have a second order Euler-Cauchy equation. And so for here, we know that, of course, x raised to the r is going to be a general solution for any equation of this type. But we need to use our characteristic equation to figure out exactly what that's going to look like, okay? So in this case here, we realize that we have an A that is 1, we have a B that is also 1, and we have a C that is -1. So we got an A, which is equal to B, which is 1, and we have a C that is equal to -1, okay? Since we're going to be using A, B, and C for our other equations here, I'm actually going to rename this so that those coefficients will look a little different. So instead of calling this A, B, and C, I'm just going to call it alpha, beta, and gamma. And let's see if I can clean this up and do that right quick. So I think that'll keep some confusion down as we move forward here. So we'll call this alpha, beta, and gamma. All right, so for homogeneous solution, we need to consider solving this equation, which means we need to figure out what our characteristic equation would be for this. And our characteristic equation is going to be of this form. Okay. So alpha times r squared plus the difference in between beta and alpha times r plus gamma is equal to 0. So using that information here, we know that this is just going to be r squared plus our beta is going to be 1 minus alpha, which is also going to be 1. So that ends up just being 0. And our gamma is going to be -1. So this just simplifies to r squared is equal to 1, which means that r squared minus 1 is equal to 0, which means r squared is equal to 1. So that means r is going to be plus or minus 1 for our roots, and therefore our homogeneous solution will be of this form. Okay, where my r sub 1, I will allow that to be -1. And my r sub 2, I'll allow that to be +1. And of course, x raised to the +1 is just x itself. And x raised to the -1 will just be 1 over x. But I'm just going to leave it as x raised to the -1 to keep things simple. All right, so now that we found what our homogeneous solution is, we need to find out what our particular solution will be. And again, we're going to do this the traditional way, okay? So we're going to find out y sub p. And of course, let's recall that y sub p here is going to be of this form, okay? So we're ultimately wanting to find out what u and v are, but we need to know what our system of equations is actually going to look like up here, okay? So we're going to go ahead and fill in the blanks for all this business here. So I'm just just going to go ahead and rewrite this here so that we can reference it later on. All right, so the first thing that we need to know is what is going to be our y1, y2, and the derivatives of those. So our y sub 1, we're just going to call that x raised to the negative 1. Y sub 2 is just going to be x. So this lets me know that my y sub 1 prime is going to be negative x raised to the negative 2. Y2 prime ends up just being 1. All right, so now that we know what our y sub 1, y sub 2, and their corresponding derivatives are, we need to identify what our g of a function will be here. And hopefully you'll see in a second why I sort of renamed those coefficients to be alpha, beta, and gamma. So our g divided by a, notice that I let alpha be 1, beta be 1, and gamma be negative 1. Okay. Now, in the grand scheme of things, let me erase this for a second. If I was to get rid of all of this, we know that what we have here, this equation, would follow the profile of a y double prime plus b y prime plus c y equals g. And in this case, we see that our a would actually be x squared, our b would actually be x, and our c in this case would be negative 1. Okay, so in using this setup for the system of equations that we need for variation of parameters, you're going to have to look at this Euler-Cauchy equation on the left side in this way. Okay, so notice here that I could write this just to kind of be clear here as alpha times x squared for a, beta times x for b, and then gamma, this here, this would be the same as gamma in this case. Okay, so the a here is just going to be in this case a 1x squared, or just x squared. So since our g here is going to be square root of x, then we know that our g divided by a is just going to be square root of x divided by x squared. Okay, or put another way, x raised to the 1/2 divided by x squared, which is just going to be x raised to the negative 3/2. And so now that we have all this information, we can actually go and solve this system of equations now. So we'll go ahead and rewrite everything with all the information in it. So we got u prime, our y1 is x raised to the 1, plus v prime, our y2 is going to be x, that's going to equal 0. Then we have u prime, then y prime, y sub 1 prime is going to be minus x raised to the negative 2 plus v prime, and then y sub 2 prime is just going to be 1, and this is going to be g divided by a, which is x raised to the negative 3/2. And I'll rewrite it one more time just to simplify everything, and then we'll actually go and start trying to solve this. Okay, So again, our goal here is to solve for u prime and v prime. And since I'm going to do this by substitution, I'm going to call this equation 1, equation 2, and I'm going to rewrite equation 1, and I'm just going to solve for v prime, okay? So using equation 1, I know that I could rewrite this as u prime x raised to the negative 1 is equal to minus v prime x. And that's just subtracting v prime x to both sides here. And then if I want to solve for v prime, then I would just divide both sides here by x. So it'll be u prime x raised to the negative 1 over x, which is the same as x raised to the positive 1. Put the minus sign over here, and that's equal to v prime. And so this would essentially be a negative u prime over x squared. Okay, so this is what v prime would be. So now that we know what v prime is, we could solve for u prime. And of course, we're going to use the second equation to do that. So for equation 2, it's going to be minus x raised to the negative 2 u prime plus v prime, which is just a minus u prime over x raised to the negative 2 again, because again, this could be rewritten this way. Let's get rid of that. That could be rewritten this way. So here we will just get rid of this and just put a minus u prime x raised to the negative 2. And that has to equal x raised to the negative 3 over 2. Of course, left side, we got two terms that essentially look the same. So we'll just rewrite it this way. And on the left side, on the right side, we have x raised to the negative 3 over 2. So solving for u prime, this would be x raised to the negative 3 over 2. All that divided by a negative 2 times x raised to the negative 2. And of course, if we simplified all that, this would end up being a minus x raised to the positive 1/2 here, all over 2. And again, that's because if we move this x raised to the negative 2 up, there will be x raised to the positive 2, and you'll have this situation here, where this is the same as 4 over 2, and if you add these exponents here, you get x raised to the positive 1/2. So that's how that ends up being that way. All right, so from here, we know that basically u prime is going to be negative x raised to the positive 1/2 divided by 2. And we're going to use that info to help us to figure out what v prime is going to be by just subbing it in. So from here, we know that v prime is just basically negative u prime over x squared, and this will be minus x raised to the positive 1/2, all that over 2 divided by x squared, and negative becomes a positive, and here we will have 1/2 x raised to the 1/2 minus 2, which will be 1/2 x raised to the negative 3 over 2. So that is what our V prime will end up being. We'll go ahead and box this off. And so now that we know, now I'll go ahead and cross this out so that we don't reference this again. So now that we know what U prime and V prime are, we can actually take the antiderivatives of both of these to figure out what U and V are respectively. And then from that, we can pretty much figure out what our solutions are. All right, so here we know that U is just going to be the antiderivative of U prime dx. And that's just basically the antiderivative of -1/2 x raised to the +1/2 dx. We ignore the constant. Here, add 1 to the exponent, divide by the same. And then we'll add our integration constant here. Plus K1. And then go ahead and work this out. And here 1/2 divided by 3/2 is just going to give me 1/3. And that'll be x raised to the 3/2 plus K1. All right, and we'll do the same thing with V. So V is the antiderivative of V prime dx. So our V prime was 1/2 x raised to the -3/2 times dx. Ignore the 1/2. And of course we add 1 to the exponent, divide by the same, and add our integration constant there. That's a 2 down there. This is a -1/2 in the denominator, plus constant, and 1/2 divided by a -1/2 is just going to be a -1. And then that will be times x raised to the -1/2 plus the integration constant. And just for clarity here, I'll go ahead and put that note that K1 and K2 are constants. All right, so now just to kind of clean things up, we know that our function U is just going to be -1/3 x raised to 3/2 plus K1. Our V is going to be -x raised to the -1/2 plus K2. And so from here, for simplicity, we drop the constants. Okay. Now, the reason why I'm dropping these constants here for this particular method is, remember that our general form for our particular solution here follows this form. And in my part 1 video, I told you that the reason why we have this form here is because our particular solution is actually coming from performing reduction of order on our non-homogeneous linear equation. And so Again, if I have y1 is a solution to my non-homogeneous equation, if I'm assuming that, then some function times x times that particular solution y1 should also be a solution, provided that y1 is actually a solution to it. Okay, so we're assuming that and then trying to basically work our way around to make things work, to force this kind of thing to happen here. And so this is why we're actually dropping those constants. Another reason why we're dropping those constants, and I mentioned this again in the part 1 video, is that if I would have kept them, then in my final answer, the K1 and the K2 that you see here actually correspond all the way back to my C1 and C2 here for my homogeneous solutions. And so I don't necessarily need to write that since I've already found what my homogeneous solutions are. So there's no need for me to actually need to write those integration constants out, because I'm just going to get redundancy basically. Okay. All right. So for simplicity, we drop the constants on these two functions here. So that's why I just have u being negative 1/3 x raised to 3/2. V is negative x raised to the negative 1/2. So from there, then life gets kind of simple. So we know that our particular solution has to be of this form. And here, I just basically write everything out from this point. So that's going to be my u. If you remember my y1, that was x raised to the negative 1. And v, that's negative x raised to the negative 1/2. And y2, that was just x raised to the positive 1. And here, if we do this, this will be negative 1/3. And this will be x raised to the 1/2 minus x raised to the, and this is a 1 here, which is the same as 2/2 positive 1/2 there. So this is what our y sub p is going to be. All right, so in seeing this, note that these two terms are like terms. So since they're like terms, I can actually combine them together here. So instead of just keeping it like this, I could actually just say, you know what? Let's just combine those terms together. And of course, if I got a negative 1/3 and a negative 1, that ends up being a negative 4/3. So to write this simplistically, this would actually be a negative 4 divided by 3 x raised to the 1/2. Okay? And that's what this actual y of p would be in simplest terms. So now that we have that, then we are pretty much at the finish line from this point. So our homogeneous solution was C1 x raised to the negative 1 plus C2 x raised to the positive 1, which is just x here. And then our particular solution would be negative 4/3 x raised to the positive 1/2. And of course, you can change x raised to the positive 1/2 to square root of x if you like, or you could leave it like this. So either way is fine. So you could answer your final answer in any one of these two ways, and both will be okay to use. Okay, so for our next example, as you see, we have another second order Euler-Cauchy non-homogeneous ordinary differential equation, but we're going to solve this by using the formula way of doing it. And this time I'm actually going to showcase what it looks like if we use the formula verbatim, which implies that we have to write out our integration constants whenever we evaluate our integrals in the formula. And so you'll see that in doing that, we'll actually come up with the we'll come up with the actual homogeneous solution there. Okay. All right, so I'm going to go ahead and just write the formula for a second order linear ODE if we were trying to solve this using variation of parameters. So our function and our variable here is a t, so we got to make sure that we watch for that. Will be a minus y sub 1, and again this y sub 1 is going to be one of the homogeneous solutions to our ODE. So we'll have this y sub 2 times g divided by a, all that over the Wronskian expression, and I'll just go ahead and write it out. It'll be y sub 1 times y sub 2 prime minus y1 prime y sub 2. So all that dt plus y sub 2 integral y sub 1 times g over a, and again same expression in the denominator here. dt. All right, so now that we have our formula down here, again we need to make sure that we know what our y sub 1 and y sub 2 are, and these are the basis functions for our homogeneous solution to this corresponding equation here. Basically let all of this, the t times natural log of t equals 0. So we're going to need to actually go through that process of finding out what the solution of the corresponding homogeneous equation is, just so that we can get our y1s and y2s, y sub 1s and y sub 2s rather. But I also want you to see that if we use this formula straight up and actually write out the integration constants whenever we evaluate the integration, that we will actually end up recovering the homogeneous part of that. So I'll be doing this first part, which is finding a homogeneous solution to this corresponding equation here for those two purposes. Okay. If you had already known what y sub 1 is and y sub 2 were, then there would be no need for you to actually go through the process of finding what the homogeneous solution of this corresponding equation would be, because you would already know it. Okay. All right, so let's find our homogeneous solution, and from that, these two basis functions as well. So we know that our homogeneous solution will look like this at the end of the day, where our C1 and C2 are constants. Since this is a second order Euler-Cauchy equation, then the equation that we are going to be trying to solve will be this one. Okay. And of course, we want to look at this when we're solving this in terms of these numbers out here. This would be alpha, this would be your beta, and that would be your gamma. The big grand scheme of things here is that alpha times t squared would be your A. Negative 2 times t would be your B. And 2 here, which is same as gamma, would be your C. And of course, this t times natural log of t, that would be your G. So we need to make sure that we specify that, because we're going to use this whenever we're implying that we're using this whenever we use this formula here, but we're going to be using the alpha, the beta, and the gamma whenever we solve the homogeneous equation here. Okay, so from here, we know that we have this corresponding characteristic equation, which will be alpha r squared plus beta minus alpha r plus gamma, which is equal to 0. And of course, our gamma in this case is going to be 2. Make that look a little better before we move on. Okay. So from that, we know that our alpha is just going to be 1. Our beta is going to be -2. And our gamma is going to be +2. So we'll just plug in that information here. So this will be r squared plus -2 minus 1r plus 2 is equal to 0. And that is r squared minus 3r plus 2, which is equal to 0. And we know the left side of that is relatively easy to factor out. We'll factor it out as the product of r minus 1 times r minus 2 is equal to 0. And that essentially just lets us know that our roots here is going to be 1 and 2 respectively. So 1 minus 1 is 0 and 2 minus 2 is 0. So from that, we know that our homogeneous solution here is going to be C1, and we'll let the first root here be 1. So I'll write it like this first. Plus C2 be of this form. And again, we're writing it like this because we know for Cauchy-Eulers, we know that x raised to the r is the general solution for those types of equations, especially the homogeneous one. And so from here, this will be C1 x raised to the 1, which is just x, plus C2 times x raised to the 2. And that means our basis functions, which is what we need to know for our formula here, is going to be just x and x squared. Okay. Now again, you could have just decided at this point that the basis functions were going to be x and x squared, but I'm purposely writing all this out so you can see how in the end, how this formula here is actually going to give us this C1 times x plus C2 times x squared. We're going to recover that in the solution for that. All right, so now let's find y of t. So notice I'm not saying let's find the particular solution now. I'm actually going to find the whole entire solution all at once now. Okay. Now, one of the things that we want to take note of is that notice that in this formula, I need to know what y2 prime is and what y1 prime is, right? So I need to figure out what the derivative of these two functions are here. And that would be 1 and 2x respectively. So we want to kind of use that as well. So our y of t is just going to be minus y1, which is x, integral of y2. And y2, that is going to be our x squared times g divided by a. And so now let's address this. So we said that here the t times natural log of t, that was going to be our g. Our a is actually everything that is in front of this y double prime here, which is alpha t squared. And of course, alpha here is an understood 1. So our a here is just t squared. So we're going to take t times natural log of 2 and divide it by t squared here. Okay. So here this will be I'll just write it in t times natural log of t divided by t squared. All that divided by my Wronskian expression. Our Wronskian expression is here. Our y1 is going to be x. Our y2 prime is going to be 2x minus y1 prime is just going to be 1 times y2 is going to be x squared. And all that dt plus our y2 is x squared integral. And now we do y1, which is x, and I'm doing x here, but this really should be t. So let me change that. So this should be t and t squared. Yeah, and I told myself to watch that and I didn't do it. So let's go ahead and make sure that we get this together here. Okay. And yeah, we need to switch all these x's now to t's as well. So once we fix all of these, we will be good to go. We shouldn't have this notation mistake anymore. That's multiplication. And lastly, let's fix these two. All right, so it looks like we got all those t's fixed here. So let's go ahead and continue. So we got t squared for y2, integral y1 is t times the g divided by a, which is t times natural log of t, all over t squared. And then, of course, all that over what the denominator here will be. And I'll just go ahead and work it out. This will be 2t squared minus t squared here. Yeah, I'll leave that and then just simplify everything in the next step. All right, so now that we have everything together here, then we'll go ahead and just work this out. Got minus t. Of course, down here, this is going to be a 2t squared minus t squared, which is just going to be t squared. And I got t squared here times t natural log of t over t squared. So we got a lot of t squareds going on over here. We'll just go ahead and reduce these two to 1 and take care of the rest of this in the next step. Here we got t times t, which is t squared divided by t squared. So all of these we're going to reduce to 1. And we'll just have a natural log of t in the numerator and a t squared in the denominator. And let's go ahead and finish up our simplification here. So we'll have negative t integral of, and of course this t and that t squared, that would reduce to just natural log of t over t dt, and then plus t squared integral of natural log of t dt, and then that'll be over t squared. And so this is what we'll be looking at to actually figure out what y of t is. So from here, we'll actually be doing our integration. Notice that for this first term, whenever we do the integration, we could use the substitution rule here, okay? Notice for this second term, the integration that's here, we can do integration by parts, okay? So what I'll do here to try to break this up so that you can follow along with what it is that I'm doing, I'll go ahead and just refer to this as two separate intervals here. So we'll call this I1 and we'll call this I2. Okay. And so we'll just work on I1 and I2 separately. So I1 is just going to be this interval here, and we're going to do the substitution rule for it. So we're basically going to say let, and I'm going to call this z, since I've already used u, v, and w already. So let z be natural log of t, and that's going to imply that the derivative of z is going to be 1 over t times dt. And of course we see we got a understood 1 divided by t times dt within here. So this implies that I1 is just going to be minus t of z times dz. And the antiderivative of z is just z squared divided by 2. And here I'm going to add the integration constant to this. So I'm going to put the k1 there. Now, of course, z is natural log of t. So this is going to look like a negative. Let's get that looking a little better. It's going to be a negative t divided by 2 times natural log of t squared plus k1. So that's what our first integral will be. Now let's work on our second integral, or second expression that has the integral in it, rather. So we're dealing with this integral here, and I'm going to rewrite it this way. So that we could use what we know about integration by parts a little bit more efficiently. So normally whenever we do integration by parts, we have this formula of integral of u dv is equal to uv minus integral v du. But since we're already using u and v, I'm going to rename it, and we're going to let u be m and let v be n. So we're going to rename it this way. Oops, yep, got that. Yep. All right, so now that we know what kind of naming I'm going to use for the integration by parts, I will go ahead and let you know what my m and my n or dn is going to be, and then just kind of move from there. So let natural log of t here, we want that to be our m, because that's easy to take the derivative of. And we're going to take the negative t squared times dt. We're going to let that be our dn. So if we do that, then here, if we use this formula, then we need to figure out what our n is and what our derivative of m is going to be, or dm in that case. So if m is equal to natural log of t, then this implies that dm, or a derivative of m, is going to be 1 over t times dt. And if dn is going to be dn is going to be t raised to -2 times dt, then I just need to take the antiderivative of that to find out what n is, and that's going to be a -t to the -1. And so now that we have that, then I know that this integral of -t squared natural log of t dt fits the profile of integral of m dn, which is going to be mn minus integral of n dm. And so from here, our m is natural log of t. Our n is going to be a -1 divided by t, basically. And I'm just rewriting that for space purposes here. Minus integral of n, which is a -1 over t, and dm. And we said our dm was a 1 over t dt. And so here, if we go ahead and just work this out, go ahead and make a new line here and finish working this out. This will be a minus natural log of t over t plus integral of t raised to the -2 dt. And again, I'm rewriting what the product of this will be after I account for the fact that subtract the negative is the same as a positive. I'm going to rewrite it like that so it's easy to do the integration for it, or specifically take the antiderivative. And this will end up being a -1 over t. And then I would have another integration constant that comes out from that. So now that we know what all that's going to be, I can take that and figure out what I2 actually is. So therefore, I2 is just going to be t squared times all this business here. Negative natural log of t over t minus 1 over t plus k2. And now I just multiply that in, and I will have a -t natural log of t for the first term, minus t for the second term, and a k2 t squared for the third term. So looking forward here, notice that, again, this is our I1, and this is I2. And so way up here, we said that our YT is just the sum of these two terms here, okay? So it's the sum of what we see here and what we see here. So what we'll do is actually go and just write all of that. And in looking at this, we know that we're supposed to be able to recover our constants, not constants, but our homogeneous solutions here. So we see how we have a constant times t squared here, but notice that we're not seeing that here. And so that means I did something wrong. Now, what I actually did wrong here is, do you notice how I did the antiderivative of this and then I added the plus k1 here? But here, whenever I started to do this next step, I didn't multiply the negative t times both terms here. And that's because this grouping symbol should actually be over here, okay? So I'm mentioning this so that if you find yourself making these kind of mistakes, you'll know what it is that you're expecting to get. So you'll kind of do a sanity check on yourself and realize, hey, I did something wrong here. Just kind of like I caught my mistake. So I'm going to erase this. And I'm going to put the grouping symbol in the right place. And by doing that, if I go ahead and distribute, I now see that this should have been a t here, and I should have a minus sign there. And so that's one way that you can kind of check yourself, because sometimes you just start writing and of course you'll forget some things, kind of like how I did there. But you see how in knowing what to expect, we can actually correct ourselves. All right, so now that we have that, notice that I have a constant times t and a constant times t squared. And that makes a whole lot of sense here because remember our homogeneous solution had to be a constant times t plus a constant times t squared. And now we're seeing that. And we see exactly what that looks like here. And of course, we have our particular solution here, okay? So now all we have to do to get our final answer here is just add all this stuff up. So let's go ahead and do that. So we know that our final solution for y of t should just be the sum of the two things that we're seeing, our I1 and I2. And I'll go ahead and just write it out as we see it and then order it in the way that we would probably want to write it out in the long run here. This is what everything is. We just write it together. And of course here, notice that we have two terms that actually have a t in it. So here what we're going to do is rewrite this as minus k1 minus 1 t. So both of these terms have t's in it. And then of course we only have one term that has the t squared. That'll be this term. And then we'll write our two terms that represent our particular solution here. And so now we can finally write our solution as c1t plus c2t squared minus t divided by 2 natural log of t squared minus t times natural log of t, where we know that our c1 is actually a negative k1 minus 1, and our c2 is actually just k2. And so this is what I meant in the first video, and I've also said that in this one too, where we don't necessarily have to do the y of h and the y of p separate, because whenever we explicitly write out our integration constants here, we're going to recover what this c1 and c2 actually is in doing all the work, if we go ahead and write out our integration constants with everything. So we know that this ends up being our final answer here. All right, so I have two other examples that I want to do. And for these last two, I went ahead and just wrote out everything because from the first two videos, you should have an idea of how the flow of all these, how this process works. So now I just want to talk more on a higher level as far as you getting a flow for how all these equations look, and we don't have to kind of go through the whole thing of, all the details of each step. So for this example, we're dealing with a third order linear non-homogeneous equation, and we're going to solve this using the formula way of variation of parameters. And so we're going to do this because we're going to utilize the formula that I talked about in the part 1 video to implement this. But in doing that, we need to find out what our homogeneous or corresponding homogeneous solution will be to this differential equation, and then find out what the particular solution would be using the formula. And of course, in using the formula, we're not going to write out the integration constants in that sense, okay, or in that particular procedure. So we see here we have a third order linear non-homogeneous equation. The corresponding homogeneous equation for this is just the third derivative of y plus y prime is equal to 0. And of course, the characteristic equation of that is just r cubed plus r is equal to 0. We go and we factor that out as much as we can. R is equal to 0, or r plus 1 is equal to 0. And the r squared plus 1 equal to 0 part gives us roots of plus or minus I. So that means that our basis of solutions here, since the two roots that come from the r squared plus 1 equals 0 situation is going to be where we get a case 3. So that's where the cosine and sine come from. Of course, with r being 0, since this is a third order linear homogeneous equation with all constant coefficients, we just have e raised to the 0, which is 1. So that's where all three of these come from. And of course, this would be the basis of our solutions, just 1, cosine and sine, and our actual homogeneous solution will be just constant plus C2, which is another constant times cosine plus another constant C3 times sine. Okay. So now from here, our particular solution, we're noting what our basis functions are for our differential equation. And because of that, we need to take the derivatives of these as well. So the derivative of 1 is 0, derivative of cosine is minus sine, derivative of sine is cosine. So we have all of that. And we also recognize that our g divided by a in this case is going to be the same as g, which is just secant. And of course, if we come back up here, we'll actually see that. So even though in your text, a lot of times they won't label this first thing as a whenever the order of the differential equation is more than 2, but I'm just going to kind of write it like this: a plus b plus c plus d, like this, and then you do your g. So basically this secant here is what your g is, and your a is the understood 1 that's right there. So this is why here I just say that g divided by a is the same as g, which is just secant x. So in the part 1 video, I mentioned this formula that you see here, and we're actually using it now, where this function w of x is called the Wronskian. This is basically the Wronskian matrix, which is a determinant of all of our functions in the first column and its successive derivatives all the way till whatever the highest derivative is minus 1. Okay, and so we use this formula here. Again, Wronskian is just going to be the determinant of this 3 by 3 matrix, and the Wronskian sub k is just going to be this same determinant here. But if, let's say, I'm trying to figure out what my first variable is going to be, since k is 1, then what we're actually going to do here is let the first column be replaced by all zeros except for the last entry, and that last entry will just be what g divided by a is, which is secant. Okay, and so you'll see that I actually do these calculations here. So our Wronskian for a 3x3 matrix is corresponding determinant. Since I have these zeros here, I can literally say that I'll say 1 times and then cross out this row or the column in that row, and then just take the determinant of this sub matrix here. And that's all I have to do, since I have these 2 rows here that begin with zeros. If I went down this way and took the determinant using the same kind of thing that I'm doing here, I would just get 0 for both of those. So do all that, do the computation, I just get 1. I know that my n, which is the highest order derivative for this, is 3, since it's a third order linear ODE. So I find Wronskian sub 1, which you see how I've let my first column be replaced with all zeros except for the last entry, which is secant x. Let everything else be the same, take the determinant of that, and I end up with secant when I work that out. When I do the other 2, of course, you see here, this is the row that gets replaced with 0, 0 secant. And for the Wronskian sub 3, the third row is the one that gets replaced with 0, 0 secant. Everything else about the Wronskian determinant would be the same. And of course, I get -1 for the Wronskian sub 2 and negative tangent x for Wronskian sub 3. And so now just using that formula, and I'll go back to it just to make sure you see it. So each term is going to look like this. Well, the first term will, this will always, in this case, be a 3 for this problem. So I have -1 raised to the 3 plus whatever entry or term we're at. And of course, times y sub k, and then we'll do the integral of the Wronskian sub k divided by the Wronskian dx. So here, we're plugging everything in here. This is what it looks like when k is equal to 1. This is what it looks like when k is equal to 2. And this is what it is when k is equal to 3. And don't know why that didn't come out okay, but all right, so from here we just substitute everything in. So we know that -1 raised to the 3 plus 1 is positive number, so it's just 1. Our Wronskian for all of these is going to be 1, 1, 1. And of course, we found out that our Wronskian sub 1 was secant x, Wronskian sub 2 was -1, Wronskian sub 3 is negative tangent x. And then from there, we just integrate as needed. So the antiderivative of secant is just natural log of the absolute value of the sum of secant and tangent plus our integration constant. And so notice here that since we're using the formula and we could not write out the integration constant since we already have what the homogeneous solution is. But again, I'm trying to showcase that we recover that whenever we use the formula. So this is what the k equals 1 result here is for the term. This is what it looks like for k equals 2. We take the antiderivative of -1. It's just going to be negative x, and then of course times cosine. And I went ahead and taken the negative cosine and multiplied it times both terms, meaning this result here, which is just minus x and the integration constant, I get K2 from that. So here is the K equals 3 part. And of course, I take the antiderivative of negative tangent. It's going to be minus natural log of cosine, or I could rewrite that as natural log of secant, if you want to do it that way, plus our integration constant here. And then from that, at this point, we're just kind of simplifying here, trying to simplify what we can. And main thing here is that I got a negative times a negative here that gives me a positive, and negative times a positive here gives me a negative. And then from that, I'm just ordering everything in the way that I need to make it look like homogeneous solution plus particular solution, where all of this ends up being my homogeneous solution, and all of this ends up being my particular solution. And again, I'll rewrite it in the traditional form using the C's here for the homogeneous part, just to show you how everything links up. All right, so for the last example that I want to do, this example is showcasing a problem that we did in a previous video that I've done for you. If you watch my video on solving non-homogeneous linear equations, and particularly of second order, by using method of undetermined coefficients, this was a problem that I did in one of those videos. And so in looking at this, what I'm wanting to show here is that although variation of parameters isn't necessarily used for these types of problems, where our g of x, our force function, is something other than a polynomial, exponential, or sine and cosine function, I want to show that we can actually use variation of parameters for those types of functions that we can actually use via method of undetermined coefficients. Okay, so this was our problem that we originally had, and we found out that the solution to that particular equation here was this. And so all I'm trying to do is show you that we can get the same thing by using variation of parameters. Okay, so we start off by knowing that since our ODE is of second order and is linear, then we know that our solution can be characterized as a homogeneous solution plus a particular one. Our homogeneous solution is going to look like this. Our particular solution is going to look like this, where the C1 and C2s are constants, but the U and V are functions of X. Okay, so we start off finding our corresponding homogeneous solution to this equation here. So we just have left side equals 0. Our corresponding characteristic equation, since all of our coefficients are constant values, is just r squared minus 5r plus 6. That equals 0. Factors out to r minus 2 times r minus 3 equals 0, which means our two roots are 2 and 3, which means our basis functions are e raised to the 2x and e raised to the 3x, which means that our homogeneous solution is of this form, where we do any linear combination of e raised to the 2x and e raised to the 3x. Okay. Now, to find our y sub p here, or our particular solution, I'm electing to do the traditional way here of doing this, and I'm going to use Cramer's rule once I get down to having to solve for u prime and v prime. Okay, so if I do the traditional way, then I need to solve this system of equations here. And I'm noting everything that I know at this point. I know what my y1 and the derivative of that is, my y2 and the derivative of what that is. And I also know that my g divided by a here is the same as g which is 4 times e raised to the 2x. Okay. And again, if you didn't recognize that, we'll go back to problem here. Notice that we have an understood 1 here, and that's where a is. If we sort of write out what this is in general, and see that g is equal to 4e raised to the 2x. So if I take that divided by 1, it just gives me 4 times e raised to the 2x. So that's how I get that. We also know here that u is just going to be the antiderivative of u prime, and v is going to be the antiderivative of v prime. Okay. Now, when I solve this using Cramer's rule, what I'm inherently doing is figuring out what the root function will be, and I could do the whole integration constant thing here whenever I figure out what u is. But again, in doing that, that will allow me to recover what my homogeneous solution part is going to look like. Okay. So we've already gone over what Cramer's rule does. So we just know that, hey, if I have u prime, I'm going to do Wronskian sub 1 divided by the Wronskian based upon the information that I have here. To be able to figure out what u prime is. And of course, my u prime ends up being 4. So the antiderivative of that is just going to be minus 4x. And if I was being formal and writing out the integration constant, I would have negative 4x plus an integration constant. I do the same thing with v prime, do my Wronskian sub 2, which means that it's the same as a Wronskian in the numerator, but I replace the second column, since this is a 2, with 0 and g divided by a. And of course, if you actually work all that out, you'll see that it ends up being just y1 times g divided by a over e raised to the 5x. Plug in what I know y1 to be, e raised to the 2x, g of a, 4e raised to the 2x, and work it all out, and I see I get 4e raised to the negative x. So if I take the antiderivative of this is going to be negative 4e raised to the negative x plus another integration constant. Okay. So from that, my y of p, which is going to be of this form, okay. And remember, we said that, where was it? We said it, yeah, so we said it up here that we knew that y of p was going to be of that form before we began. And so we're literally just plugging in everything that we know. So our u is negative 4x plus k1, and that's being multiplied times y1, which is e raised to the 2x. So that's why we see the e raised to 2x in both of those terms. And for our v times y2, we see that v ends up being a negative 4e raised to the negative x here. And our y2 ends up being e raised to the 3x. So if you're looking here, if we were to multiply this e raised to the 3x here times this v here, the e raised to the 3x times e raised to the negative x would give you a e raised to the positive 2x here. And of course, 1 times a negative 4 will give you a negative 4. So that's how we get that first term. The second term, of course, your k2 times y2. So that's k2 times e raised to the 3x. This gives you k2 e raised to the 3x. Okay? And so now, at this point, we have everything that we need. We have our homogeneous terms in here with the k1s and the k2s. We also have our particular solution terms as well. And so notice here that we have e raised to the 2x, x times e raised to the 2x, e raised to the 2x, and e raised to the 3x terms. So these two terms here would combine together. And so this would look like k1 minus 4 e to the 2x if we were writing that out. Of course, this would be k2 e to the 3x here. And this would be the minus 4x e raised to the 2x here. And you can kind of see how all this comes together just to be c1 e raised to the 2x, which is this here, because this k1 minus 4 is the same thing as c1. Our c2 e raised to the 3x, that's this term here. And of course, the minus 4x e raised to the 2x, that's this term here. Okay, so this concludes the second video for variation of parameters. And so if you're interested, the third video that I will make will be explaining how does variation of parameters work. In other words, we're going through the derivation of how we actually end up with the systems of equations and what they look like and why they look the way that they do. So that will be what the part 3 video will be all about. Again, if you're taking a differential equations course, especially if it's an introductory one, you may not need to know this information. But if you're kind of like me, you really can't grasp and retain things without really understanding the background for it. You may want to watch that because it may help you to actually be able to retain and understand what's actually going on whenever you use variation of parameters.